Here's where we actually do the experiment. The experimental apparatus is a ramp with an electromagnet at the top, actually the two of them, when we can race two balls, but the ball falls down the ramp and it hits this beam, which is broken, and stops the timer. So what happens is I push the button here, or a kid pushes the button, which is more like what's going to happen, which zeroes the timer. The ball sticks to the electromagnet, the button's released, the ball falls down the ramp, and the timer is turned off when it reaches 0.33 seconds in this case. So what we have to do is to measure the height, measure the distance that the ball goes, and then we measure 3 timings of the ball falling down the ramp. From that we can calculate the average time, and then we calculate the average velocity over the path down the ramp. And I'm going to show you this ramp a little closer from the end, more closely from the end. This is the ramp, and at the top you can see this electromagnet that I wound myself anyway. It's pretty weak, but it'll do. And then at the bottom you've got an LED, a white LED shining a light at this mirror. It comes back to the sensor. It's a cadmium sulfide photosensor, and so when the ball breaks this beam, the voltage across the photosensor changes and it stops the timer. So that's how the apparatus works. Now we're going to put this back up over here, and we're going to make some measurements on the apparatus. The first thing we're going to do is measure how the height of this ball when it's sitting on the electromagnet. Okay. This isn't going to be easy. I think some kid's going to have to hold that thing up there, because I'm not sure it's going to stay put. But it's about 42 centimeters. 42 centimeters from the table to the top. Now, it crosses the finish line. It's 5 centimeters high. So it's 42 minus 5 equals 37 centimeters of height change. Now the distance the ball actually goes between the electromagnet and the finish line is shown here. It's on a scale like that. So I'm going to hold the ball up there and make a measurement on how far it goes, which is the front of the ball, which breaks that beam. The front of the ball breaks the beam, so I'm going to hold that there, and it's right at about 41.7 centimeters. So that's the distance that the ball goes from when it's released until it turns that timer off. So now we're going to go ahead and do the experiment. I'm going to do it 3 times. And the timer's running now, but I'm going to stop it in a second, and then we're going to time the ball falling. Okay, I'm going to do it 3 times. Okay, that's 0.35. There's the button. 0.34 and 0.35. So it's 0.35, 0.34, and 0.35. So the average if you use a calculator and you round it up, it's going to be 0.35. The average velocity over the ramp then is the distance, 41.7, divided by the average time, 0.35. That gives you the average velocity, 119 centimeters per second. Now the instantaneous velocity is twice the average velocity in this case. Again, I'm not going to prove that, but it is, which is 238 centimeters per second. Now, let's repeat the experiment with a smaller ball. You're going to do it 3 times like we did before. .36, 0.36, 0.36. So the average is 0.36. The distances are the same, 0.36, 0.36, 0.36. The average is 0.36. The average velocity is 41.7 divided by 0.36, which is 116, which is 232 centimeters per second instantaneous velocity. So the distances are the same because we didn't change anything except the ball. 0.36, 0.36, 0.36. Average time is 0.36. Now note that I did not remeasure that ball. To the front of the ball, it's a little bigger distance because the big ball sticks down the plane a little further. So that may account for that 100th of a second, but that's a pretty good agreement. 238 and 232 centimeters per second. Now, we're going to move the plane down and repeat the experiment. And the first thing we're going to do is, of course, measure the height. The length, or the distance, is the same because we're going to use the big ball. So that is about 24 centimeters. And the height of the finish line, which you have to subtract off from that, is 3.7. So we're going to put that down here like this. So it's 24, and this is 3.7. Alright, so it's 24. This is this experiment here. So minus 3.7 is 20.1. I think this is actually 23 point. Just a minute, let me redo that. As I recall, I was wrong about that last time. Let's remeasure this. Oh yeah, it's actually 23.2. 23.2. So this is 23.2. That's 23.2. I don't know if you can read that. Anyway, this is 3.7. So if you do the subtraction, it's 19.5 centimeters. The distance from the finish line is still 41.7. And so what we're going to do is we're going to run the experiment 3 more times. Okay, it's 0.52, 0.53, 0.53. And that averages out to 0.53. So this is 19.5 centimeters high, and it gives you a speed, average time of 0.53. The average velocity is 41.7 divided by 0.53. 41.7 divided by 0.53 gives you 79, which is times 2 would be 158 centimeters per second. Now what we're going to do is we're going to move this thing down to the lower position. We're going to start halfway down the ramp, but we're going to put the ramp back up here so we can get about the same height change, but with a vastly different slope. And we're going to find out if the slope changes the velocity of the ball at the bottom of the ramp. Okay, so what we're going to do, put the ball on there. I'm going to measure that height. And that height is about 23 and a half. I'm sorry, is that right? 23 and a half, but this distance is 5, 4.7, it's 4.7, it's 5. So this is 23 and a half, and this is 5. So if you subtract those two, you get, what, 18 and a half. So this height difference is pretty small, so we would expect the velocities to be sort of similar with these two sets of situations. So let's do our experiment one more time, and that'll be all we're going to do today. It's 0.25, 0.26, 0.26. So that means that the average is 0.26. And this distance here is just shy of 21. It's 20.8. This is 0.26, 0.25, 0.26, which averages to 0.26. Now that 20.5 divided by 0.26 gives us 79, which is exactly the same. And 158 centimeters per second. This should have been a little bit slower, but it was exactly the same. But anyway, it just illustrates that the slope of the ramp doesn't make a difference if energy is conserved. So that's the crux of the experiment. When the kids actually do it, I want to have a few more experiments so they can switch off and each kid gets a chance to do some function with the experiment. But that's the crux of it. If you think that's doable by a third grader, just please give me a call, or if you don't, please give me a call so I know what's going on. Thanks a lot.